Stoic.
So you guys balanced a lot of equations, or we talked about balancing equations. And so actually, when you balance, when you went ahead and came up with a set of stoichiometric coefficients, so you had the same number of each type of atom on either side of the reaction arrow, i.e. when you balance the equation, then actually you know relative amounts. That's to say you know amounts of all the reactants and all the products, relatively speaking, that would be involved. Okay, the stoichiometric coefficients. I like to think of them on kind of an atom or a molecule basis, but we can scale it up to moles, okay, as well. I think we talked about that. Okay, so stoichiometry is basically the relative amounts of reactants and products that you have. Oh yeah, I guess we are, because now we're going to talk about it. So, for instance, when magnesium reacts with oxygen to form magnesium oxide, in order to balance it, you need coefficients of 2, 1, and 2 respectively, okay? Then you have the same number of magnesium and oxygen atoms on either side of the reaction arrow. When I go to balance that, I think of basically magnesium atoms, an O2 molecule, and magnesium oxide formula units, right? But we could also think of it in terms of, again, counted particles, but moles of counted particles. We could also say that 2 moles of magnesium reacts with 1 mole of O2 molecules to form 2 moles of magnesium oxide formula units. Okay. So we're counting on that. So stoichiometric coefficients are what you use to balance the equations that you turned in today. And when you do that, you are saying relative number of particles of each reactant and product involved. Okay? So that's why I like to say it's kind of like a recipe. That's to say, if you want to look at the reactant side, that's like your ingredients to your brownies, etc. If you want to look on the product side, that is your brownies, right? So it's relative amounts involved in the reaction. So stoichiometric calculations are basically going from the amount of one reactant or product to the amount of a different thing that's a reactant or product. That's all stoichiometric calculations are. But by golly, in order for you to work stoichiometric calculations, you're going to need to go ahead and have a balanced equation to work from. Because we're going to see that we're going to use the stoichiometric coefficients in the balanced equation to work stoichiometric calculations. You can't say stoichiometry too many times. Okay? So, so we're going to use the whole fact that the stoichiometric coefficients represent moles of stuff in order to work our calculations. So I have an example coming up here. For instance, if we look at this relationship between the 2 reactants, magnesium and O2, forming, and the product, magnesium oxide, we could come up with some, they look like conversion factors, okay? They actually could have come from equivalency statements. We could say 2 moles of magnesium is equal to 1 mole of O2 in this particular case. And for every equality like that, you can get 2 conversion factors. There they are. We could pick another pair of stuff. So for instance, now let's pick on magnesium and magnesium oxide. We could say 2 moles of magnesium is equal to 2 moles of magnesium oxide. We can make 2 conversion factors out of that. Of course, one is the reciprocal of the other. And the other thing we didn't talk about was the O2 and the MgO. Okay? So we could say 1 mole of O2 is equal to 2 moles of MgO and come up with 2 conversion factors. Okay? These actually are stoichiometric ratios. The word's right up there. Stoichiometric ratios, stoic ratios. And actually, yesterday in the calculations that you're going to need to do for your sodium bicarbonate lab, I put stoic ratios. These are what they are. Well, not these, but for the different reaction. So let's go ahead and work a couple of problems dealing with this reaction. Okay, and we're going to start out with kind of the heart of the stoichiometric calculation, and then we're going to kind of go broader. You'll see what I mean. So let's go from, and when I read these, a lot of times I will diagram underneath here, okay, what the problem says. So for instance, how many moles of oxygen, so I'll put question mark moles under the O2, how many moles of oxygen is needed to react with 2.45 moles of magnesium. So I'll find my magnesium and put 0.245 moles underneath that. So basically that says what you have, what you know, and what you're after. Okay? Not too bad. So actually, can you see, this is how we would knock this problem out. Oh, are we going to do two? Oh, yeah. Then we're going to do it, that was the first problem. And the second problem, let's go ahead and write it underneath where it goes to. The second one is how many moles of MgO, so question mark moles of MgO, okay, can be produced. Now, this actually, number 2 is kind of follows number 1. So we are assuming then still with regard to magnesium, we have 0.245 moles of magnesium. It's not the best written problem in the world, but that's okay. So in other words, we know this amount, and in the problem number 1, we're after moles of O2. In problem number 2, we're after moles of MgO. That's it. All right. So let's knock those two out. Again, this is just the heart of what we generally call a stoichiometric calculation. So we can go from moles of magnesium to moles of O2, okay, using one of those, was there 6? One of those 6 ratios a few slides ago. And we're going to pick this one. Here in a minute when I work it, actually, I'm going to start with that 0.245 moles of magnesium over 1. And you see where if I pick this stoichiometric ratio, my moles, units of moles of magnesium are going to cancel. Okay, I'm going to be left with units of moles of O2, which is what I'm getting to. Okay, so that works great. What doesn't work, actually, is if we want to try to use that ratio, and this actually should be, let's see, what's wrong with this? I guess. Oh, this will work, sorry. So in the second problem, I got ahead of myself. In the second problem, we're going from moles of magnesium to moles of magnesium oxide, okay, and we're going to use the different ratio. So again, we're going to start with that 0.245 moles of magnesium over 1. We're going to insert this ratio so that actually moles of magnesium again cancel. We're left with moles of magnesium oxide. That's it. That's how we're going to work the second problem. It should be pretty easy. Like Donald Trump. Should be easy cheesy. So to work the first one, we put the thing we want to convert, 0.245 moles magnesium over 1. And then we introduce the stoichiometric ratio. So one of the things as we get rolling, sometimes students lose track of, is remember where these numbers came from. These numbers came from the coefficients, the stoichiometric coefficients. Okay? All right. No uncertainty brought by the 1 or the 2, so we round to 3 sig figs, and we have 0.123 moles of O2. Pretty good. A similar thing for the bottom one. We start with 0.245 moles of magnesium over 1. Now we need to use the 2 moles of magnesium oxide over 2 moles of magnesium. Moles of magnesium cancel. We're left with units of moles of magnesium oxide. Now, sometimes students will say, but Mrs. Snipes, you're just being silly. Why do you want to go ahead and put a 2 over 2? Why not just recognize that they're equal and go with 1 over 1? I would argue that the numbers 2 over 2 bring more information. Of course, those numbers came from here, right? So units of moles of magnesium cancel. We're left with units of moles of magnesium oxide. And, of course, we get the same number, right? Okay. So, again, when we work our typical stoichiometric calculation, that's going to be the heart of the calculation. So when I think of heart, I think of kind of the middle. So that's to say you're going to have something before that and something after that. Because usually you'll have a problem like this. So let's kind of write underneath the species what we know and what we're after. Okay, it says what mass of oxygen. So I'll find oxygen and put question mark grams. What mass of oxygen is needed to react? And then it gives me grams of magnesium. So under magnesium, I'm going to put 0.30 grams. Okay, I'm a picture person. So basically, we have 0.30 grams of magnesium. We need to know grams of O2. This actually might be ringing a bell as to yesterday's lab, when basically we knew the grams of what? Your sodium bicarbonate, and needed to find grams of CO2. So here we go. This was the slide I thought we were after a minute ago. We know that we can pick the right ratio like we did before and go from moles of magnesium to moles of O2, okay? But you cannot go directly from grams of magnesium to grams of O2 using those stoichiometric coefficients in the stoichiometric ratio. You just can't. So instead, and this is kind of like the flow chart, like I gave you how to work this sort of problem, the flow of it, like I gave you yesterday. You're going to go from grams of magnesium to moles of magnesium using its molar mass. Molar mass of magnesium, one of my favorite phrases. And then you're going to go, then you'll be to the heart of the stoichiometric calculation where you go from the moles of what you know about, which is moles of magnesium, to moles of O2 using that stoichiometric ratio. Stoich ratio. And then once you have moles of O2, you're ready to finish off the problem and go from moles of O2 to grams of O2 using the molar mass of O2. So I'll say this a few times and then hopefully I won't have to check it wrong. You have to show, you don't have to show calculating the molar mass of magnesium, but honestly, the fact that the molar mass of O2, what would you do? You'd go to the periodic table, find out what the decimal number for oxygen is and multiply it by 2. Show that, okay? Show that. Don't make me count that wrong.
Can you restate that?
Sure. In order to go from moles of O2 to grams of O2, you need O2's molar mass. And so you're basically going to take 2 times 16.00, which actually reminds me of another thing, O2's molar mass. Whenever you have like some elements like oxygen are just, oh my gosh, 16.00, really? Yes, that means that actually you know it out, the uncertainty begins in the 100ths place. You need to go ahead and make sure you write that whole thing. Don't truncate it. Okay, so let's work this. So I've gone ahead and I have all the molar masses here. You wouldn't have to show molar mass of magnesium in 24.31 grams per mole, but you could. But you do need to show the next two. So for oxygen, it's 2 times 16.00, or 32.00 grams per mole. And don't forget your, is this for me?
Yeah.
Thanks. Don't forget your units. And so for magnesium oxide, you take 1 times 24.31 plus 1 times 16.00, and you get 40.31 grams per mole. So this is kind of like the front end stuff before you sit down and kind of string up some terms and knock it out. So let's string up some terms and knock it out. So we start with the thing, that 0.30 grams of magnesium. Now, we need to be explicit. You can't just put 0.30 grams. Okay, you have to put 0.30 grams mg. OMG. No, you really do. Okay, so now we need to convert it to moles, so we're going to use the flipped version of the molar mass of magnesium. So 1 mole Mg over 24.31 grams Mg. So again, so I'm afraid you're going to have to be explicit there. Of course, if you were kind of keeping up, sometimes it's nice to keep up with what units cancel as you go. Right now, if we were to stop, we have units of moles of magnesium. So now we're ready to go from moles of magnesium to moles of O2. So now this is going to be our stoichiometric ratio. We're going to put 1 mole of O2 over 2 moles of magnesium. Just remember, and you know, if you haven't done too many of these, just remember where the 2 comes from and where the 1 comes from. Okay. All right, so units of moles of magnesium cancel. We're almost there. We have actually units of moles of O2, and we want to get to units of grams of O2. So here's where we introduce that molar mass of O2. So we have 32.00 grams of O2 over 1 mole of O2. And then finally, you know, moles of O2 cancel, and we're left with grams of O2. So, voila! And taking one last look at it to how we need to round it, to me, it's looking like 2 significant figures in the mass of magnesium. Actually, we have 4 significant figures in the molar mass here for magnesium. This brings no uncertainty, and actually we have 4 significant figures in the molar mass of oxygen. So it's looking like 2. So I get, showing 2 significant figures, 0.20 grams O2. Yay! So that is a stoichiometric, that's the normal stoichiometric calculation. You're going from grams of something to grams of something else. Okay? Sometimes chemistry problems have a whole bunch of different ways you can work them. The phrase, how to skin a cat, different ways to skin a cat, actually that came from skinning a catfish, not from skinning little kitties. I looked it up one time because I was like, that's terrible. So this one, though, there's probably only one way to work it. You know, it's kind of straightforward. Some students might want to break it up, but I kind of like stringing them up because it kind of gets you ready for stringing other things up. Okay. So, okay, let's work another one. We still have the same mass of magnesium, that 0.30 grams of magnesium, but we're after something different there. 0.30 grams of magnesium. It says what mass of magnesium oxide is formed. So magnesium oxide, I'll put question mark grams. And this is actually something we're going to talk about on Monday. Notice it says that the other reactant, the thing that's reacting with magnesium, is there in sufficient amount. What they are saying is there's sufficient amount, there's enough O2 to go ahead and make all of that magnesium go away, be reacted. Sometimes, and we're going to use this term again on Monday, but sometimes we say this is probably in excess, or if it's just the right stoichiometric amount, but usually it's in excess. Okay, so we're ready to go from 0.30 grams of magnesium to question mark grams of magnesium oxide. Here we go. Oops, I forgot. So just let's go ahead for kicks and give us a game plan. So we're going to go from grams of Mg to moles of Mg using magnesium's molar mass. And then we're going to go from moles of magnesium to moles of magnesium oxide using the stoichiometric ratio, stoich ratio. And then we're going to go from moles of magnesium to grams of moles of magnesium oxide to grams of magnesium oxide using its molar mass. So here we go. The first term is going to be that 0.30 grams of magnesium over 1. Then just like we did before, we're going to use the flipped version of the molar mass of magnesium, 1 mole mg over 24.31 grams of mg. And then we're going to introduce a stoichiometry ratio. If you're kind of keeping up with what's left, we want units of moles of magnesium on the bottom, and we want units of moles of magnesium oxide on the top. This is actually, sometimes I will actually write the units and then go up in the balanced equation and find the coefficients. Sometimes I'll write these units and then go up and find the stoichiometric coefficients. All right, so moles of magnesium cancel. We're left with moles of magnesium oxide. Now all we need it to use is the molar mass of magnesium oxide, which a few slides ago we said is 40.31 grams per mole. So 40.31 grams MgO over 1 mole of MgO. And kind of for the same reason we had 2 significant figures last time, we have 2 significant figures this time. So the mass of magnesium oxide that will form with 0.30 grams of magnesium is 0.50 grams magnesium oxide. So some of you are already thinking, and I have it coming up here in a minute, some of you are already thinking, well, by golly, when you knew this is 0.30 grams, in the first problem we came up with 0.20 grams, okay, of oxygen, you automatically knew that according to the conservation of mass and conservation of matter, you already knew that that should be 0.50 grams. And you're right. But it never hurts to check. So I would use that more of a check, and sometimes students will say, well, Mrs. Snipes, if I have an example like that on a test, can I go straight for by difference getting the other reactant? And I say, if you ever had one like that on a test, you could. But I never give one like that on a test. So, but yes, you definitely can. I would use it as more of a check than getting the right answer. Okay? Sweet. All right, so we looked at this one before. I have some, seems like some deja vu slides, right? Where P4 reacts with Cl2 to form PCl3 in this way. So this is balanced with coefficients of 1, 6, and 4, kind of across the board. And we looked at those videos successfully recently, so that's good. It's highly exothermic. A lot of energy released. So let's do a stoichiometric calculation with this one. Okay, so what mass of P4, so I'll find my P4, put a question mark grams under there. What mass of P4 is needed to react with 1.25 grams of Cl2? And if you're like, oh boy, this just feels like we've done this, and we have. We're going to do just a few more in class, and then we're going to consider it good. Okay, so basically then we're going to go from, I don't think I outlined it here, but we're going to go from grams of Cl2 to moles of Cl2 using the molar mass of Cl2, and then we're going to go from moles of Cl2 to looks like moles of P4 using stoichiometric ratio. And then we are going to go from moles of P4 to grams of P4 using P4's molar mass. That's it. So I don't know if you have all these on your slide, but I went ahead and knocked out for P4, it's 4 times 30.97 is equal to 123.88 grams per mole. For Cl2, it's 2 times 35.45, and that's equal to 70.90 grams per mole. And for PCl3, it's 1 times 30.97 plus 3 times 35.45 is equal to 137.32 grams per mole. You'd be like, Mrs. Snipes, we don't need the molar mass for PCl3. Not yet, you don't. Okay, so yeah, we only need the first 2 molar masses to work this problem. But one of the things I struggle to try to get students to focus on, I've already said it a few times, is that our stoichiometric ratios can only come from the stoichiometric coefficients. Okay? All right, so let's work it. So we're going to start with that 1.25 grams of Cl2 over 1. Next thing is to go ahead and convert it from grams to moles. So we're going to use what I call the flipped version of the molar mass of Cl2. 1 mole Cl2 over 70.90 grams of Cl2. There's its molar mass. And of course, grams of Cl2 cancel. We have units of moles of Cl2. Now we're ready to skip to the moles of P4. Okay, and like I said, sometimes I'll show you what I'm trying to say here. Sometimes for this term right here, I literally will write mole Cl2 and I'll write mole of P4 on the top. I literally will do that. And then I go up to my thing up here and I put a 6 down here, 6 moles of Cl2 on the bottom, and I put a 1 mole P4 on the top. That's really how I do it, because it's I'm less likely to make a mistake. So those big numbers, that stoichiometric ratio, use the stoichiometric coefficients. So units of moles of Cl2 cancel. Now we're just ready to finish up the problem to go from moles to grams for P4. So now we use the non-flipped version of the molar mass of P4, which a few slides ago we said is 123.88 grams of P4 for 1 mole of P4. And so unit-wise, everything is canceled except for units of grams of P4. To me, it looks like I am limited by the grams of Cl2 to 3 significant figures. So we get 0.364 grams of P4. You know, so if you were keeping track, and actually you might want to, so we have 1.25 grams, and now we have 0.364 grams, and you're right, the next problem, or the second problem, number 2, we're actually going to go after grams of PCl3. You may be like, just add them together, and you're right. Okay? All right. Here we go. What mass of PCl3 can be formed from the reaction of 1.25 grams of Cl2 and sufficient P4? So I'm not going to diagram it out this time, but I am going to go ahead and put 1.25 grams under the Cl2, and I'll put question mark grams under the PCl3. But you're going to get your chance. Here in a minute, I'm going to turn you loose on a problem, so in class. Okay, so here we go. We're going to start with 1.25 grams of Cl2 over 1. To work these problems, one way to think about it is if you're like, I can't remember how to work it. Well, make sure that you keep the species with the masses and the molar masses, 1.25 grams Cl2 over 1, and just kind of make that your first term and go from there. So we're going to use the flipped version of the molar mass of Cl2 like we did before, 1 mole of Cl2 over 70.90 grams of Cl2. So units of grams of Cl2 cancel. We're left with units of moles of Cl2. Now we're ready to jump from the Cl2 to the PCl3. So again, just to kind of emphasize, I would do this third term here, I would put units of moles of Cl2 on the bottom, because that's what I want to cancel. And I put units of moles of PCl3 in the top because that's what I want to be left with. Okay, and then only then would I go up and I would snag the 6 and make it 6 moles of Cl2, and I would snag the 4 and make it 4 moles of PCl3. It's like a recipe, okay? It's relative particles. Mole is the number of particles, so it's relative moles works too. So at that point, moles of Cl2 have canceled, and we're left with units of moles of PCl3, but we want grams of PCl3, so we know that we can use the molar mass of PCl3, the non-flipped version, which is that 137.32 grams per mole. So 137.32 grams PCl3 over 1 mole of PCl3, and then our moles of PCl3 cancel, and we're left with grams of PCl3. Looks like 3 significant figures again. So I get 1.61 grams of PCl3. I believe the next slide is a mass balance check. Oh, no, it's not. Good. Did you have a mass balance check? Okay. Well, there you go. The next slide actually is, we're going to talk about it just a minute, and then I'm going to turn you loose. I hope everybody has a calculator or a phone to do some calculations on, and I have my calculator. I'm going to show the answers to these. But like I said, I just like to take a few minutes in class, talk with your neighbors. So remember stoichiometric calculation, you're given the grams usually, of just anything, and you're asked to find the grams of something else. So we have all sorts of possibilities. We have what? 2 reactants and 3 products, right? All sorts of possibilities. And kind of the key amount that's given, we're actually going to go with a product. We're going to say, all right, you have 0.143 grams of O2 is produced, okay? And actually we have 4 calculations to do, and they look like this. Okay, so for each case, for all of those cases, we have this amount is known, 0.143 grams, okay? So for problem number 1, okay, it says what mass of each reactant. So of course the reactants are on the left. So for problem number 1, basically your question mark grams of TiO2, question mark grams of BRF3 based upon that mass of the product. Okay, actually just to kind of make sure we're on the same page, we'll call that 1A. And we'll call the second one 1B. And problem number 2. Okay. Again, it goes to the 0.143 grams of O2 produced. What mass of each of the other products would be produced? So for problem number 2, A, we're going for the grams of TiF4. And for problem number 2B, we're going for the grams of Br2. So there are definitely 4 problems there. So before I turn you loose, you have on the next slide all the stuff you need, okay? So Merry Christmas, right? So these are all the molar masses you'll need to work those 4 problems, right? So I'll give you a little bit of time, kind of walk around and put them up here. And actually, they won't be exactly equal because of rounding, something like that, but they should be close. And like I said, use it as a check. So homework that's due are just 2 problems, but you know how that goes. So we'll take a look at these 2 problems. These will be due on Monday. And they look like oh, wait a minute. What did I call it? One more. There it is. Dang. Okay. So here's 17, and so it's got 3 parts to it. And unlike the ones we worked, they kind of mix it up for what mass. The mass is given of something, and it's different. So for instance, A is how many moles. Now notice A finally is kind of like a not the ordinary stoichiometric calculation. It's just short. You've got to stop at moles. Don't take it all the way to grams. So how many moles of O2 can be produced by the decomposition of 32.8 grams of KClO3? So again, you're going to have to show those molar masses. I'd kind of just get in the habit of showing the molar masses up front, do the stoichiometric calculation. The next one, so I went ahead and showed how to do it. I don't know if you need that or not. And then the third one. They're all kind of similar. So how many grams of KCl are formed if you also form 28.3 grams of O2. So that's a stoichiometric calculation going between 2 products. The next one, 18, is also got 3 parts to it. So I think you'll do fine. And I didn't put the hints over here, but I don't think there's any, nothing tricky about it that I know of. Okay? All right. So that's all I got.